Morning. Today we are going to discuss the last homework. Okay, so let me show you the all. Okay. First of all, I want to show you the number one. Let me show you the homework. Yep, it was the homework 15. So we are going to discuss the MA1 using the simulation. And then we are going to go back to the data, the valve one. The reason why I put the MA1 parameter is negative 0.07705 because from the data above, we chose the MA1 model as with the parameter is a negative 0.7705. So I want to do the simulation from the MA1 model from the valve data, and I want to show you what is the good one. So let me go back to the all again. Okay, here. So let me make the data. Let me make the data using the function of the ARIMA simulation, and put the list one is order. Before when we use the data set above, we took the log transformation and the difference. So that means it's already we took the log transformation and we took the difference. So now in the simulation, we just set up it's a no AR part, it's a no difference, but only the MA1. Okay, because before it's already we took the difference. So I want to compare to the after the transformations, and the MA parameter is negative. It's a 0.7705, and I generated 1,000 random samples. I think something wrong. Sorry, I missed the close the parentheses. Is here. Okay, so I made the data. So let me plot the data. So it is the pure is MA1 model, right? And then using the sarima function, sarima using the data. And now again, yeah, we don't have to take the difference, and even we don't have to take the log transformation because later I will explain to you again, but it's already we took the transformations. So simply the 0, 0, the 0, 0, and 1. And we don't need the constant. So say the no dot constant is equal to true. Okay, it's good. So now here's the output. Yep, here's the output from the sarima function. And oh, I'm sorry, I was wrong. See, I missed the decimal point. So let me generate the simulation again. It's a negative 0.7 and do the sarima. Okay, now here is the as negative 0.74. Yeah, we set up it's negative 0.77, but it's a random sample. What I want to show you, yep, is this picture. Okay, so here's almost random noise and no correlation, and it's almost the normal distribution because we generate it's a pure MA1. we generated 1,000 random samples from the pure MA1 model. So what I want to show you is this picture, the p-values. As I told you on last Monday, the p-values must be bigger than 0.05. So when we fit correctly, it's a good ways, then we have to get the last picture. It looks like this. It's all p-values. It must be bigger than 0.05. So that is what we want to get is at the end in the step of the diagnostics. So now let me try again. Using the BARV data. It is number 2. So in number 2, I suggest to you the trying again with the BARV data. So let me try the sarima, but it's a take the DIFF. It's a log VAV. In this case, you plug the 1 here in the middle, because we did 1 here and no difference 1, but either ways it will be fine. So we tried the either way and we checked the either one will have exactly same output. So let me try again this way using the DIFF function here, right? It's no 1 here because already we took the DIFF here. So see, in this case, yeah, it's exactly, we took the estimation from the data set. It's negative, it's 0.7705. And please look at the diagnostic picture. It's almost the white noise and no correlation. Here is a little bit 1 here, right? But it's almost nothing. And it's almost the normal distribution. But the problem was the p-values, all p-values is less than 0.05. So it was the problem, okay? So when I plot the A shift, I'm sorry, I gave you the, it's a wrong name of the function. It's a ASF. It is not the name of the function. Yeah, I'm so sorry about that. So A shift 2 and difference, log, again, and VAV. There's one more. Yes. So definitely from the A shift and PA shift, there is a 1 peak at 1 in the A shift, and the PA shift is decreasing, exponentially decreasing. It's a trade-off. So definitely from the 2 functions, we have to take the MA1. But you know, the MA1 is not exactly same thing. Let me show you the A shift, PA shift with the data set we generated today. The data was it's a purely MA1 model. So please remember this picture, the A shift, PA shift from the VAV1, and let me plot with the data we generated today, pure MA1. Yes, it is a data set. Yeah, see, it's almost the same. There is a 1 peak, it cut off at 1, and is exponentially decreasing. It's a trade-off in PA shift. So from the A shift, PA shift, we have exactly same pattern from the pure MA or from the data is above. But when I make the diagnostics picture for the data, it's so good. The p-values is all p-values is bigger than 0.05, but the data, the VAV, is not so good. So we have to do is a little bit more. So we don't have any reason. We don't have any reason. I just add the AR part. If you want to ask me why, I'm sorry, it's no reason. I just adjust. I just adjust a little bit. I just add the AR part. Definitely from the A shift, PA shift, MA1 is the best choice. But from the diagnostics at the end of the feeding procedures, we don't have as good pictures for the p-values. So simply just add is one more is the AR part. Then now, yeah, it's so good. You know, before we had is a little bit is out of the band is something in the A shift of the residual, right? But is we don't have anything and p-values is much bigger than 0.05. Is everything is good. And also the MA1 parameter is negative 0.77, but now it is a little bit lower. It's a 0.08858, and we added is one more as parameter for AR part. So it is a positive 0.233. And let me, yes. So it's a somehow, so it's definitely the ARMA, the ARIMA 111. In this case, even though it's a 101, but we took the difference. Remember that? Yeah, before here, we took the difference. So it's exactly this picture is from the ARIMA. It's 1, 1, and 1. Does it make sense? Right? So it's definitely the ARIMA 1, 1, 1 is a better model is than ARIMA 0, 1, and 1. Okay, it's because of the p-value. So it's finally, it's a white noise. It looks like the white noise, and it's everything, every A shift of the residuals in the band, and it's almost normal distribution, and p-values is much bigger than 0.05. So we're done. You know, it is exactly looks like the white noise. That means when we take the log transformation and when we took the difference and we delete the AR trend and delete the MAA trend, then now the residuals is purely a white noise. So we're done. So as absolutely the final model will be again is ARIMA 1, 1, and 1. So do you have any question? Okay, so now let me show you the diagnostics picture for the white noise. So in number three, I gave you a statement is SRIMA, and using the all norm. You know, the function of all norm is the random number generator, the random number generating function from the normal distribution. So just to generate 1,000 random numbers. And I want to show you the diagnostic picture from the random, the white noise. And I want to compare to this one. Is the diagnostics plots from the ARIMA is 1, 1, and 1 for the valve data. So I wanna plug is actually I wanna make the pictures from the random noise, the white noise. So exactly the white noise was the MA1 model. So it's the 0 for AR, no difference, and just one parameter for MA model for the white noise. So please look at this one, the old one, from the data, from the model of the ARIMA 1, 1, and 1. And let me click the enter. See, it's almost the same. It's a white noise and no correlation among the residuals. And now it is the exactly normal distribution because we generated 1,000 random samples from the normal distribution. So it is a more closer, right? Can you see that? And please look at the p-values. It's almost the same patterns. It's all p-values. It's much bigger than 0.05. So now so let me go back to this one. From the data, the valve data, right? Yeah. So it means after we feeding after we feed in the ARIMA 1, 1, and 1, the residuals now is a purely the white noise. So you can compare this picture and another picture from the white noise. Then you can see it's now the residuals will be the white noise. So that is what I want to show you. And number 4 and 5, I gave you is another example from the GMP data. So let me plug. That is also in the homework number 15 is I gave you just log GNP and 0 and 2 first. Yeah, here's a 1 and 2 because okay, let me plot the GMP first again. Yeah, it is increasing. As you can see, it is increasing. So we need the difference. We need the difference because always the increasing time series is not a stationary. So we just take the difference. Yeah, it looks good. It's wiggling. It looks like the white noise, but the problem is later we have a bigger variance. So because of that, we have to take the log transformation as well. Yeah, but yeah, it's later is a good one, but it's before. Yeah, you know, because of the log transformation. Can I take the natural log ln? Ln is not a function in. Yeah, I have no idea what is the. I think the log is a natural one, but anyway. So as before, we take the log transformation and the difference again on the GMP. So now, let me estimate using the sarima. Be careful. It's now I take the difference here using the function of the DIFF. So now the parameter is must be 0, 0, and 2. Because again, let me make the ACF too. ACF and the PACF. In this case, the reason why we chose the MA2, because here's the 2 peaks in ACF at 1 and 2. You know the lag, please look at the lag 1. The lag is here is 1 and 2, 3 and 4, because it's actually, it must be 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. Every 4 legs, 4H, but it gives us this 1 here, 2 there, 3, 4, because it is the quarterly data. So let me show you something here. Let me just type the GMP. Let's look at the data. Yes, can you see here? Yep, in 1947 to 2002 is actually a quarterly data. So because of that, the lag numbers is here is not 4 but 1, and it is not 8 but 2. It's because it's a quarterly data. But anyway, it doesn't matter. So there's a 2 peaks, and here's another peak here. So you know, actually, we have to choose. In this case, it's cutoff and cutoff. But unfortunately, in the table, it's before we discussed how can we choose the model. We didn't have the cutoff and cutoff. You know, actually the ARMA model had tails off and tails off. But unfortunately, this one is a new pattern. It's cutoff and cutoff. So because of that, we just try first MA2 because we had 2 peaks in ACF. So let me try the sarima. Again, yeah, it's already we took the difference. So it must be 0, 0, and 2. And also it's no constant. It's true. It's good, right? So here's the 2 parameters for MA2 model. And this one is the diagnostics. It looks good. The standardized residuals, and it's good. Yeah, it looks good. The A shift of the residuals and the normal distribution is looks good, but the problem was all p-values is less than 0.05. So it is not good enough. So because of that, we try again AR1 model, because there was one peak. There was the one peak in the PA shift. So that means the AR1 might be the good one. So let me try the AR1, but it's the same thing. And here's a peak in the residuals, right? Its normal distribution is okay, but the p-value is still less than 0.05. So I think it's because of this one. It's because of the correlation is among the neighbor residuals. I think the MA2 is better, but still the p-value were less than 0.05. So why don't you try just a second. In number 5, I gave you the same one, the same as the first one in number 4. I'm sorry. It must be this one. It's the AR1 and MA2. Okay, so the number 5 must be this one, so you can try it later. See, it's a little bit different. There is an error, right? Yeah. You know, as I told you, in the S-ARIMA model, even the ARIMA function is S-ARIMA function or ARIMA function, always they are do the iteration to get the correct answer. But I think in this case, finally it converts to something, but it's probably it's non-stationary. Yeah, you know, the ARIMA is actually, it is the model of the ARIMA 1 because we took the difference here. So it's exactly, it is the ARIMA model 1 and 2. It's not the stationary. Okay, so it is not a good one. And another choice is another trial is apply the ARIMA 0, 1, 2 with the constant. Okay, sometimes it's because of the constant, but we just put no constant. But just to say it's a false, it's no constant false means we just add the constant, right? This one is a little bit better, right? So before, when we did not put the constant means the intercept is in the regression model. But when I add the intercept, yep, here is the x mean, yep, is average, the constant is additional estimation. It will be the ARIMA 0, 1, and 2, right? It's one difference, and MA2. Even though this one is almost a 0.05, but yeah, but at least as many of them is bigger than 0.05. And also, let me try again AR1 with the constant. Say the false here. Yeah, yeah. Is also the p-value is getting bigger than 0.05. So now it is the ARIMA model 1, 1, 0. But how do you think which one is better? You can comparing the ARIMA 0, 1, and 2, MA2 1, right? And this one is the AR1. The ARIMA is 1, 1, 0. It's for me, I think this one is worse because when I try this one, ARIMA 0, 1, and 2, the p-value is a little bit bigger. You know, always the bigger p-value is better. Okay, so today, I want to show you again is how can we do the diagnostics. And finally, this one is the best picture. You know, we generated the random samples from the white noise. Yes, this one. Yeah. So ideally, we want to get these pictures because it is the pure the white noise. It's everything is bigger than is a 0.05. But one of them, it's a couple of them is close to 0.05 is fine because it is random numbers and it is random data. But it's at least it's all most of the p-values is much bigger than 0.05. And remember, this one is the diagnostics pictures, diagnostic plots from the white noise. So that is what we want to get. So we done. Then now we finish the diagnostics. Then now the next step is the forecasting. So again, at first, we plot the data first. So we have to look at the pattern. So if it has an increasing the trend, then we have to take the difference. And it does not have the constant variance. And then simply we can take the log transformation. And we have many kind of other transformations, but in this examples, we took the log transformation and take the difference. And then plot the A shift and PA shift to choose the initial model and trying to estimation and then diagnostics. And we just adjust it a little bit for the models, right? Then when we finished the diagnostics, so we can say we have good models. Then now we can do the forecast in the future. So that is the procedures in the building models in time series is using the ARIMA. We have one more meeting on Friday and one more homework today. I will email you is the last homework about the seasonality, the seasoning. Okay, so it will be the last topic, and we are going to discuss the topic, the homework on Friday. And I'm thinking about the final exam. The final exam will be almost the same as this. Yeah, I will generate the random numbers, the random data from a model, and you try to make the plot, A shift and PA shift, and estimation and diagnostics, and try again. It's adjust and forecasting. So yeah, so the final exam will be is similar as the homeworks, the recent homeworks. Okay, so let me think about the final exam data. But anyway, I will give you the homework number 16, and it will be the last one. It's regarding the seasonality, and we are going to discuss the seasonality on Friday. So, do you have any question? If you don't have any question, you can leave. And as Brandy, do you have any question?
Yes. So I couldn't do the homework. I don't know
Okay.
why, but I'm gonna try to go to the library and download R and do the
Okay,
homework.
just a second. You just stay. Yeah, we can do together. You and I is after this
Mhm.
meeting. So please don't quit. And
Okay.
any other people? Any question? Yeah, if you don't have any question, yeah, Rachel.
I was wondering what day or time our final exam would be on.
It's maybe I think it's maybe I will email you on next Monday. And but you have your own final exams in the final exam week next week, right? So I might give you as more than a day. Yeah, even though as I will email you someday, but I will give you enough times. It's a couple of days or 2 or 3 days. Then it's whenever you have time, then try do the final exam, and you just it's email me, then that will be good. Okay. Okay, so if you don't have any other question, you can leave and have a good day. And I will email you. It's another homework. Thanks for coming. Okay, Brandy.
Yes.
As now I have only 7 minutes because
Uh-huh.
I have a 40 minutes limit. So let me close. Let me close this meeting and immediately I will open again. So please sign in on your computer
Okay.
because you can show me as I show you. Do you understand what I'm saying?
Mm-hmm.
So please sign in on your computer where you can use the all and please show me, okay?
Okay.
So let me out and sign in again.